There are many things that make me positive that God is a mathematician. One of them is he's so good at keeping track of debits and credits, a true accountant. So Jesus says that anybody who even gives a drink to somebody will not lose their reward. So if you hold the door open for someone, God notices and he has a plan for how that will be rewarded. If you smile at a grocery store clerk when they're obviously having a bad day, some sort of reward's coming. If you stay up with a roommate and help them talk through a relationship problem, reward for that coming. I don't know how, I don't know when, but it's coming because God is a mathematician. This lesson is the second part on time series. The Excel notes file section time series 2 is posted. And just like its predecessor, time series 1, it's going to use this section 4.0 CM1 spreadsheet. Let's review from the last lesson, the time series 1 packet. So we had a financial measure that's graph over time looked like this. We decided to fit a linear model and got these residuals. Notice that there was a pattern in the residuals and said, well, I think we can do better. And we decided to tackle that with a model of this form, where the prediction would not just be a linear model of time, but actually, as one of the predictors, would include the previous value of the series itself. So using a series past values to predict its future values. And so we did that and got an improved model. We ramped it up a bit and used not just the previous one, but the previous 2 values of the series. And that seemed to be still a better model. And we concluded by pointing out that this does definitely seem to be a good predictor using 2 lagged values of the series. So going to the new material, the thing that I want to address here mainly is how do you decide what order of model to use? Should you just go 1 time step into the past, 2, 3, 4, how many time steps? There are several ways of deciding that. One of them is with autocorrelation, so let's talk about correlation in general. So if I have 2 paired quantitative variables, maybe a person's height and weight, and then I have a whole group of 100 people or something and their height weight pairs, the correlation between those 2 is a measure of both the direction and strength of their relationship. So it's going to be a single number. And let's see. For example, here, there aren't coordinate axes drawn, but I can think about it being this way. And if the person's height were given on the horizontal axis and weight on the vertical axis, we might see a set of data looks like this. Taller people tend to be heavier, not always, but tend to be. So we could calculate the correlation. I'm not going to mention the formula here. But for example, in this graph, the correlation turns out to be 0.9, a positive number. But here might be the situation, for example, if we had a sample of cars and we knew that their weights and the gas mileage that they got. So weight on the horizontal axis, gas mileage on the vertical axis. And overall, we can see that heavier cars tend to get lower gas mileage. In this case, R would be a negative number, like maybe negative 0.7, for example. And then just some other examples. A picture that looks like this, where there doesn't seem to be much pattern at all, R would be 0. Here, it's a little hard to tell, but there's a slight negative pattern, R equals negative 0.2. This is a little larger correlation, positive, maybe R equals 0.5, and here is a strong negative correlation, it's going to turn out that R would be like negative 0.99. So I'm not going to talk at all about the formula for computing R, but we've been talking about R squared a lot, and it's no accident that we use that notation. R is just the square root of R squared if I have a model relating these two variables, say weight and height. And it's not both, it's one or the other, the plus root or the negative root. We know that R squared is between 0 and 1, and so the R value itself is going to be between -1 and +1. Positive R indicates positive correlation, negative R, of course, negative correlation. And there's an Excel command that we can use to compute that. If I have paired data with one variable in A1 through A10, the other variable right beside it in B1 through B10, then the correl or correlation command giving the two data sets will compute the numerical value of R. Now we're talking about time series, and so we want to specialize this to autocorrelation. So what this means is that I take the value of a series and its lagged version and correlate those two. So the series itself and say k time steps in the past, how does that work? For example, we'll go here in, let's see, here in a moment, but here is the series itself, and here is its lag 2 version. What's the correlation between these two variables is what autocorrelation is talking about. And in Excel, you can use the correl or correlation function. Just have to be careful to get the ranges right. I'm using the same column each time, but shifted down in the rows. We'll do an example of that in just a moment. And the reason I wanted to talk about autocorrelation is it's one of the ways that you can choose the so-called order of the model. So an order K time series model would be to use the previous K values of the time series to do prediction. If K equals 1, then I just am using the single previous value. K equals 2, I use 2 values, and so on. And one of the ways to choose the best order is to just keep trying. Choose K equals 0, no time dependence at all, other than the linear relationship. K equals 1, K equals 2, and last time what we were mainly doing was looking at the residuals. So when we used K equals 0, just the linear fit, we got residuals that look like this, which didn't look random at all. We used K equals 1 and got residuals that looked more random, but still not perfectly so. We used K equals 2 and got residuals that still look more random, and so on. So you just keep trying until the residuals look pretty random. Of course, along the way, you're doing linear regressions to compute these models, so you can also be looking at the R squared, or better yet, at the adjusted R squared. And what you typically see is that as you increase the order of the model, the R squared goes up, and then eventually levels out, or maybe even starts to go back down. And you're looking for the highest possible R squared, of course. A different way, usually less work, is to fit the linear model first, compute the residuals from the linear model, and then start computing the autocorrelation of various orders for those residuals. And what you're looking for here is that the autocorrelation would get fairly close to 0. So let's look at this CM1 data. Here's in this sheet is the original data. In this sheet was the work that we did last time with computing the lags and the models for the predictions for the lag 2 model and so on. And now there's a new tab, autocorrelation. What I've done here is take the original data, compute the linear model, slope and y-intercept, give the predictions, and compute the residuals. So we are at a position like this. I just computed these residuals. Now let's start looking at correlations. So here is autocorrelation order 0, autocorrelation order 1, order 2, and so on. For autocorrelation order 0, I just take the correlation between the series values, all of them. They are in cells F2 to F38, notice, with itself. Well, the correlation of a set of data with itself is going to be 1. All of the values are equal to themselves, so of course there's a perfect positive relationship. For order 1 autocorrelation, so now I'm computing the correlation between the following sets of data. So this is going to be a lag 1 correlation. So I use all of the data except the very last item. That's the first set of data that's going to be correlated. And then the second set of data is I skip the first one and use all of the rest. So another way of saying that is that I use the first, let's see, there are 37 data values. I use the first 37 data, the first 36 data values here with the last 36 data values. Same thing as saying I use the series compared to its lag 1 version. And the autocorrelation turns out to be 0.75. Okay, that's smaller. That's good. I'll keep going. So then I use F2 through F36, drop the last 2, and then drop the first 2, compare those, and get autocorrelation 0.38. Okay, this is good. They're still going down. I'll keep going. 3 stages of lag. So order 3 autocorrelation 0.18. Keep going. 4 time steps lag, autocorrelation 0.01. Okay, now that's getting small indeed. 5 steps of correlation. Notice what's happening. Oddly enough, the autocorrelation has turned negative and it's going back up in size. Autocorrelation 6, order 6, negative 0.43. So I don't much care whether the correlation, autocorrelation is positive or negative, but I do want it to be as small as possible in size. And so this model would suggest, or this approach would suggest, that I use a order 4 regression model. In other words, a model that includes n-1, n-2, n-3, and n-4 as predictors. And we just decided an order 4. So why is the order 1 correlation, autocorrelation, for example, so large? Well, that's talking order 0. Let's talk first. That's here, and you can see that a data value is very much related with the data value nearby. This guy is big and positive, so this guy tends to be relatively big and positive. This guy is large and negative, so is this nearby data point. But the farther the lag goes, the less relationship there is between this guy and this guy, or this guy and this guy, and so on. Notice that there's no single best way of doing this. The autocorrelation approach is one way that you can go about choosing the order. And here are a couple of others. And it's kind of a matter of experience and trial and error and preference. The only other thing I want to mention is that it is possible to use other trend functions other than a line. So we've been talking about a linear trend, but if I saw a time series graph that looks like this, where there's a lot of jagging up and down, but overall there's a trend that goes up, 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 and then turns maybe back down again, it might make more sense to fit, say, a parabola to this model than a line. So I might use a model, for example, of this form with a linear and a quadratic term and one lag coefficient. There's no magic way of choosing this trend function either. You look at the graph, most likely, or some previous theory that you have and say, I know that this should be roughly parabolic overall, or whatever your data is telling you. And we will stop there.